So 4.2 part 2, completely randomized experiments. All right, so a completely randomized design, the treatments are assigned to all the experimental units completely by chance. And some experiments may include a control group that receives an inactive treatment or a baseline treatment. So one thing I just want to be clear about is an experiment is any situation in which the experimenter is applying treatment to the subjects. Now, a good experiment will always have comparison, right? It'll have a control group and a treatment group, but there will be sometimes you'll see like multiple choice questions where they give you a prompt and ask you if it's an experiment or an observational study. And even if there's not a control group, if treatment is being applied, it's still considered an experiment. It would just be a bad experiment because there's no basis for comparison. But anytime you're applying treatment, that is an experiment. So this is a design outline or a design diagram. And again, we went over this in one example last time. Totally fine to use. I like them because it helps me get an overview of what the experiment looks like versus I think writing things out. You're allowed to just write it out when you're asked to design an experiment. You can just write it out verbally. It ends up being kind of long-winded and difficult. And I think the design diagram lets you kind of organize your thoughts a little bit better. But remember, the things that you have to describe are: how are you going to conduct the random assignment? And then basically, what is being measured? Now, for something like this, where they are, I don't know what this experiment is, but it seems to be how do students do when they study online versus in a classroom for an SAT score? It's pretty obvious here what's being measured, right? SAT scores, but just make sure that's clear. So if you need a further verbal description, go ahead and give that. All right, go ahead and give me a green check when you're good with this slide and we will move forward. And so this is just what I said. This is an AP exam tip I took out of the group. You won't get full credit for providing a diagram like that. You're expected to describe how treatments are assigned to experimental units and then clearly state what will be measured or compared. All right, did we already do this? Is this the example we did? We did this one, right? Okay. Oh boy. Okay, well, just a reminder, I'm going to draw out the diagram real quick, and you guys already wrote this down, but this was a situation in which we had 64-year-olds and okay, we wanted to see how they reacted to different stimuli, basically. So the design diagram looked like this. We would go here to random assignment. Treatment 1, treatment 2, treatment 3. Measure, measure, measure. And then compare. And so you could use this as your baseline design diagram, and then off to the side you would just want kind of a key describing the few key things that you need to receive full credit. So the first one being random assignment. The easiest way to do random assignment is not going to be using a random number generator. And our text, they suggest using the hat method just because it's easiest to describe. So like here, I could say label 60 slips of paper number 1, 2, and 3 for 20 slips each. Place in a hat and mix well. That's a key step as well. So when you use this kind of hat method, you have to make the statement mix well. That's the randomization. And then have each child select a slip. Children receiving slips with a 1 receive treatment 1. Okay. So describe the random assignment. If you labeled the diagram the way I did, like you didn't actually write out what the treatments are, you would then want to make sure you state those treatments. So treatment 1, treatment 2, and treatment 3. So let's say treatment 1 is fast-paced. Programming. Treatment 2 is slow-paced. And treatment 3 is drawing. And then you would want to state what you're measuring. So measure and that what we're measuring is impulse control after treatment. Okay, so I realized that was redundant because I included that example in the last notes, but just coming off of break, making sure that you hit these things and understand how to describe an experimental design. All right, I do think I threw some new ones in here, so let's check those out. Okay, single blind and double blind experiments. So let's talk about double blind first. In a double blind experiment, neither the subjects nor those who interact with them and measure the response variable know which treatment a subject received. So there are two parties that don't know which treatment was received. So the reason we need this is sometimes you need a third party to diagnose your subjects when you're testing something. So in this case, I want to be clear, the experimenter is different from the person who is measuring the response. So this would be like a drug company testing a new drug, right? They would need, so let's talk about the vaccine. The way that they're testing these vaccines, right, is they took the Moderna one, they took a sample of 30,000 people. They gave half of them the vaccine, and then they gave the other half just a placebo, so just like saline solution or whatever. And they just want to see whether the vaccine works better than the placebo effect, because we know that if you think you receive treatment, your body can have a psychosomatic response. Like it'll actually respond to thinking, your brain thinking it receives some type of treatment, even if it was just saline. So I want to see if the vaccine works better than that. But they can't have the people know which treatment they received, whether they received just saline or whether they received the vaccine, because that would negate the placebo effect. Also, the drug company, the experimenters themselves are not doctors, so they cannot diagnose necessarily whether or not somebody has COVID 19. They need a doctor to do that diagnosis. Um, it's a little more black and white with a vaccine, right? Because you can do just like a blood test or um, a nasal swab and objectively discern whether somebody has COVID 19. But for something like a pain pill or something that's just symptomatic and you're having the doctor diagnose it based off of symptoms, it's a little more subjective. So you wouldn't want the doctor to know whether the patient they were diagnosing received the treatment or the placebo, because that could influence the way the doctor diagnoses the patient. Does that make sense? So in that case, you want the patient to be blinded, meaning they don't know what treatment they received, and you also want the doctor to be blinded, meaning they don't know whether or not the patient received the treatment or the placebo. That's a double-blind experiment. Single blind is just the subjects don't know. The experimenter and the doctor could know in that case. All right, give me a green check when you're good with this slide.
Mr. Toller,
Go ahead.
when the vaccine experiment finished, did they then tell people whether or not they actually got the vaccine or not? Because
it's a great.
then
I don't
have
know.
to know
I would think they would have to, but I also had that question. I was talking to a buddy of mine who had a friend in one of the trials,
Mm-hmm.
and I was like, "Yeah, but she doesn't know whether she received placebo or treatment." He was like, "No," and I was like, "Did ask her if they're gonna tell her at the end of the
Yeah,
trial?" I would imagine they would have to because you would need to know whether or not you need to
you
now
need the
go get the
vaccine.
vaccine. Yeah. All right. Okay. This is a weird example, but it illustrates. Oh, sorry, my computer is lagging. It's not. Let's go. Change slides. One sec. Change the IP on me. There we go. Um, all right. So here, in an interesting experiment, researchers examined the effect of ultrasound on birth weight. Pregnant women participating in the study were randomly assigned to one of two groups. The first group of women received an ultrasound and the second group did not. When the subjects' babies were born, their birth weights were recorded, and the women who received ultrasounds had heavier babies. All right. Did the experimental design take the placebo effect into account, and why is this important? So the answer here is no, it did not. But it should, and this is a little bit counterintuitive, right? We think of the placebo effects with drugs, but not necessarily with something like an ultrasound. Like, how would the placebo effect work in that case? And the reason it might be important is, you guys know what an ultrasound is? They basically use like echolocation to get a three-dimensional mock-up of what the baby will look like, right? And they do that just by shooting ultrasonic waves, so just like sound waves. The issue here is a lot of times the ultrasound is like the first time a mother may see her child or connect with the child. And so just receiving that ultrasound could possibly cause them to systematically care for themselves or for their baby differently than maybe a mother who never receives an ultrasound, right? So maybe So I'll say this: mothers receive an ultrasound could systematically differ in variables like health, from those who don't. Right? So a mom who's going to get an ultrasound, maybe a mom who cares for their child more, or has the forethought to get pre-birth health checks and things like that. And they may systematically differ from those who don't. But if what our experiment is truly setting out to do is to see if it's the ultrasound causing the babies to be heavier, we would want to account for this. So we would need a placebo group, and that would just basically be a group in which the doctors gave the moms a fake ultrasound. So they would give half of them a fake ultrasound, have a fake baby on the screen that's not their baby. So the mom thinks they're receiving the ultrasound, but they're actually not. Now, it's insanely complicated. We're going to talk about something that in experiments like this that are looking to seek academic recognition and be published, you first would have to submit your experiment to a board of ethics, and this would be a completely unethical experiment. You can't tell pregnant women that you're giving them an ultrasound and show them a fake baby and tell them that that's their baby. But the point of that is that's how you would include a placebo effect and truly be able to make sure you accounted for that variable I wrote down in number 1. Was the experiment double blind? So this wasn't even single blind, but the one that I described would have to be a single blind experiment. You would expect that even if they included the placebo group where the tech was giving half the mothers a fake ultrasound, the tech would have to know whether or not they were truly switching on the machine, right?
Mr. Toller,
Go ahead.
let's say you actually did want, like, your point was to measure the effect of, like, the psychological effects of having an ultrasound on, like, how you cared for a child. Then would you still want, like, a control group if that's, like, what you were measuring is, like, that effect?
So how would you create an experiment to measure that effect? Well,
Yeah.
I don't know. So I don't know if, well, in that case, then you would want, I guess, a group that you gave ultrasounds to and a group that you kept from getting ultrasounds, right?
Oh, okay.
But if you're trying to, so what I'm getting at is here, the way they've worded it, they're trying to see if it's the actual ultrasonic waves that are causing the baby's birth
Oh,
weights to be heavier.
okay.
All right. So an improvised design for this experiment, again, unethical, but for the sake of just statistical experimental design, if what you're trying to do is suss out whether ultrasonic waves cause a heavier birth weight, you would need that placebo group. So I would say assign Okay. So I just described what I would do, which is assign half the mothers a true ultrasound and half a placebo where they receive a fake ultrasound, and then compare birth weights. All right, give me a green check when you're good with this page. We're getting pretty close to finishing this up. All right, so what does it mean for a result to be statistically significant? Statistically significant means an observed effect so large that it would rarely occur by chance. And a statistically significant association in data from a well-designed experiment does imply causation, meaning there's a cause and effect. So large that it is unlikely to have occurred by random chance. All right, give me a green check when you're done with this one. All right. So I'm going to walk you just through an experiment that was to find out if talking on a cell phone is more distracting than talking to a passenger. It says researchers at the University of Utah conducted an experiment in which they had 48 undergraduate students participate as subjects. They randomly assigned 24 to drive on the simulator while talking on the phone, and the other 24 to drive while talking to a passenger. Then they measured how many of the drivers in each group missed a rest stop that they were instructed to stop at prior to beginning the simulation, and the results are below. What I want to know is, are these results statistically significant? And to find out, let's see what would happen if just by chance we were to randomly reassign the 48 people in this experiment to two groups many times, assuming the treatment received doesn't affect whether a driver stops at the rest area. And so what we're saying is, let's say that out of the 48, these 15 were going to miss the rest stop no matter which group they were in. Okay? So what I'm saying is, okay, let's pretend for a second that those 15 people were just going to miss the rest stop. They're just forgetful people, right? And it didn't matter if they were on the cell phone or if they were talking to a passenger. So what we could then do is create a simulation where I go, all right, I'm going to use the numbers 1 to 48. That's going to represent my sorry, that's good. Those numbers are going to represent the people in my group. Now, numbers 1 through 15 represent the people who missed the rest stop, right? And I could then just go ahead and do a random, like use my calculator and randomly select a group of 24. I could then count up in that group of 24. Sorry, I'll randomly select a group of 24, and that represents let's say, the cell phone group. The remaining 24 numbers that weren't selected into that group would then represent the passenger group, right? Okay. And then you could count up how many in that randomly selected group of 24 were the numbers 1 through 15, right? And so that would represent how many in the cell phone group, just by random chance, happened to miss the rest stop. And then we could do this many, many times, over and over and over again, each time recording how many in the cell phone group missed the rest stop. So that's what we've done here. So if we did that 100 times, there was only one trial out of 100 in which 12 or more in the cell phone group missed the rest area just by chance. And when I say just by chance, I'm saying under the assumption that we made that those 15 people were going to miss it no matter what group they were in, right? So if we did that trial 100 times and each time recorded how many in the cell phone group missed the rest stop, there was only one trial in which 12 or more, so 1% of the time, did 12 or more miss the rest stop by random chance. 1% is very few, which means it's very unlikely that we got 12 in the cell phone group that missed the rest stop by chance, because when we conducted it by chance, it very rarely occurred. Okay. We also did this. Do you guys remember the hiring discrimination activity we did at the beginning of the year with the flight attendants? That was the same idea, statistical significance. We're going to hit this again. This was just kind of another little example alluding to statistical inference that we'll do further down the road. So if this felt a little confusing, that's okay. The only takeaway I really need you to have about statistical significance right now is that it means the outcome is unlikely to occur by chance. And if it's unlikely to occur by chance, that means it must have occurred due to the treatment, right? All right.